Okay, thanks so much. And thanks so much, everybody, for coming here. Today I'm going to be talking about the use of quantum-centric supercomputing to study the ground state properties of electronic structure problems. And this was a collaboration with our friends at RIKEN. The goal is to solve a computationally challenging problem, which is the energy estimation of, in electronic structure, and it has potential applications in the development of new materials, drug discovery, battery design, you name it. However, the usual way that quantum computing is used in electronic structure calculations may have some fairly substantial bottlenecks when we try to scale to much bigger molecular systems. So let me run a back-of-the-envelope estimation of this claim. Let's say that one wants to just use the quantum device to estimate expectation values of observables, and in particular, let's say that we want to estimate the expectation value of the Hamiltonian. Let's take as an example 36 orbital active space of this iron 4 sulfur 4 cluster. Under Jordan-Wigner, this would get mapped into a 72 qubit experiment. It would contain, the Hamiltonian alone would contain 6.7 million Pauli operators. And if we want to reach chemical precision in the estimation of this expectation value, just because of accumulation of errors, we would need to reach 10 to the minus 10 precision on the estimation of the expectation value of each of the Pauli operators. Because of central limit theorem, this means that you need to execute each circuit in the order of 10 to the 20 times, and assuming a repetition rate of the order of 10 microseconds means that you're going to spend quite a bit of time just collecting samples from the quantum device. So we need a solution to these types of scaling bottlenecks. And a particular solution that we have been working with is these sample-based quantum diagonalization approaches, where classical distributed computing enables quantum to address complex use cases with a few large quantum circuits. So let me walk you through the workflow. The starting point is that we're going to prepare a quantum circuit, here denoted by psi, on the quantum device, and we're going to collect measurements only in the computational basis. These measurement outcomes are going to represent electronic configurations, again under Jordan-Wigner mapping. And something to take into consideration is that electronic structure is a problem that is particle number preserving, so we will also use particle number preserving states psi. These measurement outcomes, bit strings that again represent electronic configurations, will be passed into the classical part of the algorithm, where they first encounter something that we call self-consistent configuration recovery. It is very easy to identify bit strings that have definitely been corrupted by the effect of noise because they just simply come with the wrong Hamming weight. So it is those bit strings that will be affected by this configuration recovery procedure, where we are going to do some probabilistic bit flipping, as I will discuss in a little bit more detail on the next slide, to be able to bring them back into the correct particle sector. After that has been done, we will look at our pool of bit strings, and we're going to do some bootstrapping. We're just going to subsample them according to the empirical distribution that we observe, and they're going to be sent into an eigenstate solver. So essentially, the bit strings are going to define a subspace where the Hamiltonian is going to be projected to and diagonalized in. So here, the role of the quantum device is to identify what are the relevant subspaces to describe the ground state physics of the problem. After we have projected the Hamiltonian and diagonalized it, we have a classical representation of the approximation of the approximate ground state. We can collect some of its properties, and in particular, something that we are interested in is the average orbital occupancy, which is going to be passed back into this configuration recovery subroutine to deal with the effects of noise at the bit string level. So let me illustrate with a simple example. How does this configuration recovery work? Let's say that we have a 4 orbital problem with 2 electrons, but because of the effect of noise, we receive a bit string that is missing 1 electron. We know that out of these 3 zeros, we need to flip one of them back into a 1. But which one should we pick? Well, we can use the average orbital occupancies, so the expectation value of the number operator for each of the orbitals, to inform the bit flip probability. So the bit flip probability can be proportional to the difference between the value of the bit and the average orbital occupancy, such that if the average orbital occupancy is high, then I know that I should flip that bit with high probability, whereas if the orbital occupancy is low, as in that case, I know that I should flip that bit with low probability. Now you may wonder, okay, but where do you obtain these average orbital occupancies from? Well, instead of assuming that we know them a priori from an approximate classical method, we actually compute them and refine them self-consistently within sample-based quantum diagonalization, as the previous slide showed. So a few properties and highlights of these types of workflows is that it allows us to deal with observables with millions of Pauli operators, like those that appear in quantum chemistry. It provides no false positives for ground states. It satisfies the variational principle, so you can rank solutions according to their energies. It relies on distributed classical computations, and the complete removal of the effect of quantum noise comes with an exponential runtime in the noise rate, as with any near-term algorithm. And its performance is guaranteed for concentrated or sparse wave functions. These are the three systems that we studied. We studied the dissociation of nitrogen in a double zeta correlation consistent basis set. 26 orbitals. This would correspond to a 58-qubit experiment, and I think around 1,500 2-qubit gates. This is just showing some of the device mappings that we use for these experiments. The second system is a 20-orbital active space of this iron-2 sulfur-2 cluster, 45-qubit experiment, 1,700 2-qubit gates. And lastly, we moved into a much bigger species, which is this iron-4 sulfur-4 cluster. The active space with 36 orbitals. This is a 77-qubit experiment with 3,500 2-qubit gates. So what results did we obtain? So let's begin with the dissociation of nitrogen in the correlation consistent basis set. Here the brown points correspond to the results obtained from this SQD workflow run on quantum devices, and we see good qualitative agreement with the baseline, which we chose to be heat-bath configuration interaction. I think that to the best of our knowledge, this is the first description of the dissociation of this molecule in a correlation consistent basis set using quantum algorithms. The second one is, again, this iron-2 sulfur-2 cluster. And here, in this case, we studied the energy variance relations of the estimate eigenstates that we were producing by these methods. In the energy variance plane, if I increase the accuracy of my method, I expect to see a linear trend if I'm close enough to an eigenstate, where upon increasing, I go to lower variance, and I'll also go to lower energies. Here we have an easy knob to tune the accuracy of the method, which is the subspace dimension where we project and diagonalize the Hamiltonian too. Again, the points correspond to the the subspace dimension here is shown by the color bar. The points correspond to the results obtained from the quantum device, and what we can see is that actually we are able to catch three eigenstates which are very close in energy. These iron-sulfur clusters are actually very strongly correlated and pretty hard to describe their low energy physics. But here we showed that we were able to catch three different eigenstates which are close in energy, and additionally the extrapolation to the zero variance limit of the third one is in very good agreement to the DMRG obtained by the Chan group. Thank you. And lastly, the point of studying this much bigger iron-sulfur cluster was to stress test this method. So not only show you the cases where we had a good result, but also where are the limitations. So again, this is a molecule which is much bigger. The quantum circuits are here. They have 3,500 2-qubit gates. And what we saw from the quantum results is, okay, in the energy variance plane, we see that the points are aligned. However, the energies are not great. They are just slightly better than Hartree-Fock. So again, here we are I think that this shows us that at least as of last year, this is where the current limitations of these methods were. However, with increased error rates, I think we have observed much better results since then. But again, the point here was to see whether we could observe, whether we could extract a useful quantum signal from the device. And to be able to assess that, we actually ran the same configuration recovery procedure and projection and diagonalization on white noise. And we saw significantly higher energies from the white noise and also not aligned. So this told us that we could indeed, even at these massive circuit scales, extract useful signals from the quantum devices. So with this, I'll thank you very much for your attention, and I'll be happy to answer any questions you may have.
All right, thanks, Javier. I'll open the door to questions.
Yeah, so the approach that you're pursuing here, it has a classical analog that's pretty well known, which is called select CI. And yet, whenever I see comparisons, you're comparing to something like CCSD or CISD. But I would think that really, if you want to understand, is the quantum computer doing something useful here, you should compare to these classical analogs like heat bath CI or something like that. Or even like at a baseline, just generate random bit strings, the same number of random bit strings that you're sampling from the quantum computer, and use that for exact diagonalization and compare. So my question is, have you done things like this? Do you have any reason to think in particular that the quantum computer is actually doing something useful in generating these configurations? And also for these methods, for these select CI methods, is the configuration generation component even the bottleneck typically, or is it typically the diagonalization part that you're doing classically anyways?
So thanks so much for that question. I think that's a very insightful question. So let me break it down a little bit. In terms of just diagonalizing in subspaces generated by random bit strings, yes, we have done that. Those are the pentagons on Fe4S4. In the paper, we also have done, for all of the systems that you see here, we've also done that, and we have observed that when we do that for the exact same subspace dimension and following exactly the same data analysis, we see higher energies. So that's why we are confident that we were able to extract a useful signal from the quantum device. Now, in terms of the comparisons against selected CI methods, this is a really interesting question, which we're exploring in quite a lot of detail. We have some points here. The crosses are heat bath configuration interaction. Also here, they are heat bath configuration interaction. I think that these results, we have not seen that we beat selected configuration interaction methods at the same subspace dimensions. I think this is something that we need to make clear. Now, another very interesting point that you brought is whether the bottleneck is in the generation of the relevant electronic configurations. I would say that it's not in the generation of the electronic configurations itself, but it is on whether you are generating subspaces whose quality is optimal, right? Whether you can find subspaces of lower dimensions that give you better energies. So I think that's where there is a space for quantum to perform better than the classical selected configuration interaction methods.
But like in heat bath CI, typically is more time spent generating configurations? Or
No. You spend a lot more time diagonalizing, but something that may happen actually is that when you try to converge it, that you need to explore subspaces which are bigger in dimension than the ones that actually span the ground state. So you need to perform those diagonalizations for the selected CI method to identify whether you have useful bit strings or not. We actually have some numerics on that, but that's also in the supplement of the archive. But thanks so much.
All right, we have time for a talk.